Okay, so this is our review for our first exam. What does the exam cover? Chapters 1, 2, and 3. All of chapters 1, 2, and 3. What was in chapter 1? Well, a lot of stuff when you look back at it, you say, we got that down. So what is the rate equation for conduction? Fourier's law. What does it look like? Q double prime equal to minus K dt dx. Or if you don't like the double prime, get rid of that. Put the A right there for the cross-sectional area. And we build on that in the next chapter and the next chapter. How about for convection? What's our rate equation? Q is equal to HA Ts minus T infinity. What are those temperatures? The free stream, far away fluid temperature, T infinity. What's our surface temperature, Ts? What is H, our convection coefficient? What are all the units of K? What are the SI units for H? Those things we should know at this point. And then for radiation, now we have Q is equal to A sigma Ts to the fourth power. Now, what's the name of this equation? It's not Fourier's law. It is the Stefan-Boltzmann. And this sigma was our Stefan-Boltzmann constant, 5.67 times 10 to the minus 8 watts per meter squared, Kelvin to the fourth. That temperature right here is an absolute temperature. It must be in Kelvin. Yes, you can get the Stefan-Boltzmann in BTUs, an hour, foot squared, etc. Rankine to the fourth power, but we don't use that in this class. It's in the textbook as well as other places if you want to work in what I call the United States customary system of units. But here, SI. Okay, so SI, there's our Stefan-Boltzmann constant. It doesn't stop at 3 digits on that. There are more digits. It's just we rounded off to 3 significant digits. All right. What is A in this equation? Area. But then that was how well it emits radiation. We haven't used this equation as much, so I'm still going to explain it now because we did introduce it. We had a property known as the emissivity between 0 and 1, and it's how well it emits. And then if you have an exchange, let's say I have a flat surface, and it sees an enclosure. I'm only interested in the top of it. The bottom is insulated. I may be interested in the rate of heat transfer going from this, let's say this is, let me get rid of this arrow here and show it up like this. Surface 1 to surface 2, which is large. And because it's large, we'll get to it. Its emissivity is essentially 1. It's essentially black. Haven't justified it, but this is a simple radiant exchange equation. Q 1 to 2, what's the net exchange between 1 and 2? The photons are leaving 1 and going to 2. The energy is leaving 1 and going to 2, but guess what? 2 is sending its photons back. So there's a radiative exchange. And so it would be the emissivity of 1, the area of 1, the Stefan-Boltzmann constant, temperature 1 to the fourth minus the temperature 2 to the fourth. That's a modified Stefan-Boltzmann equation for the radiant exchange. Just like as soon as we put that emissivity in, we really modified the Stefan-Boltzmann law. Stefan-Boltzmann law is just for black body emission. So we are introduced to our rate equations for our 3 mechanisms of heat transfer. We are introduced in the next chapter to resistance concepts. But right now we can go back and fill it in. Resistance is L over Ka, and resistance 1 over Ha. And what are the SI units for this R? Degrees C per watt. True? True. All right. We then looked at, your previous class, thermodynamics, may be a little collision of symbols. Hopefully you've gotten it straight now what lowercase q means in this textbook, in this class. We try to avoid putting dots on a lot of things that are already rate equations. But if you first looked at this coming out of thermo, you want to put a dot right there. But we don't. It's already the rate of heat transfer in watts. Okay. Units and dimensions. This is so fundamental. I'm glad they have it in a heat transfer book. I know they have it in so many other books. Don't struggle here. Master it. Master it. Spend the time if you don't already know. the value and how to handle dimensions and units, etc. How to solve problems, how to be methodological, how to be neat, how to be organized. Did I encourage you to be neat and organized? How many exams am I going to grade that are not going to be neat and organized? And the number one complaint, might as well let it be known. He doesn't give enough partial credit. I can't understand your work. Less partial credit. Help yourself earn the highest possible grade. Got it? All right. Oh, heat transfers everywhere. That's chapter 1. Very important chapter. You know, I find that people have to often go back to chapter 1. It just is true. The most fundamental chapter, the first chapter in many books, is a key chapter that we sort of skirt over too fast and we don't dig deep into it. All right. Introduction to conduction. What were the two big equations out of this? Well, Q as a vector is equal to minus K. What is this del thing? Yeah, it's the gradient operator. So we talk about scalar fields, temperature scalar fields. We talk about a vector field for the heat flux. I should put a double prime on that, shouldn't I? Because that's a heat flux vector field. And that's the generalized Fourier's law. Could we write that and express it in rectangular? Yes. Cylindrical? Yes. Spherical coordinates? Yes. All three dimensions in the spherical and cylindrical? Yes, although we almost always just use the radial in the cylindrical and the radial in the spherical. Very simple. Don't get bogged down with those thetas and phis. They can bog you down, but the most of the heat transfer problems in cylindrical and spherical are radial. All right. Now, it brings up this property known as K. What was the name of K? What are the SI units of K? What is the most common error associated with units in this class, heat transfer? It's the people will say K has units, and this happens all the time. They'll say K has units of watts per meter squared Kelvin. What is the error? Don't shout it out. Do not shout it out. I want you to write it down on your piece of paper when I walk around and check a few. I want to know if you know, without consulting your neighbor or the book, what is the error that I just wrote for the units of K? Don't shout it out. Don't help your neighbor. It's one-on-one. All right, so the most common error is right here. People will put a square on that meter. It's not needed, is it? Somebody says, well, I think it's watts per meter degrees C, not that watts per meter Kelvin. Is one right, one wrong? They're both correct. But you learned there's a difference, 273. If I want to go from degrees C to Kelvin, I need to add 273. Do we know that now about like the back of our hand? You can explain it to a friend when they make that error. All right, so there's a lot in this chapter. You have also another property, alpha. What's the name of alpha? Thermal diffusivity. And it's defined as the ratio of K over rho C. And it's more important when you do transient analysis. But what are the typical SI units on alpha? You can work it out, but can you remember? It really helps if you can remember some things like this. You look at that units and you say, I just came out of fluids. I dominated that class. I had an A+. He didn't give me an A+ grade, but I had an A+ in that class. And anyway, there is a property called nu. It's one of those viscosities, kinematic or absolute? Kinematic, and it's defined as mu divided by rho. I know what rho is, mass density. Mu is absolute viscosity. And guess what SI units it has when you boil it down to the basics? And they're the same. And yes, you can have things that have the same units, the most fundamental units, and still be different parameters. All right. So then we came to the heat diffusion equation. What is another way of saying the heat diffusion equation? What is that? It is a first law of thermodynamics. It's an energy balance. It's an energy balance where we're doing heat transfer only, no mechanical flow of energy. All right, so it's an energy balance equation, and it comes in like this. Maybe you wrote it like this. Let's put K del squared T plus Q dot equal to rho C partial of T with respect to time. Why does he have the funny derivative here, not this dt dt like that? Why not? What's the difference? Partial versus ordinary. Meaning temperature now is more than dependent on one independent variable. It depends on two or more. Time and space. Maybe T and X or T and R. So we have a PDE. All right. If you divide through by K, then you get 1 over alpha. You get 1 over alpha partial of T with respect to time equal to Q dot divided by K plus del squared T. Hey, what is the name of this del squared T? What's another name of that? The Laplacian operator. Absolutely correct. Is it the gradient of the divergence of temperature, or is it the divergence of the gradient of temperature? Which is it? Clicker's not working today. Okay, we're going to do the old-fashioned clicker. That's called your hand. So we go version A is correct or version B is correct. All in favor of A. All in favor of B. All right, you're just being sheepish on me. It's the divergence of the gradient. That's the Laplacian. So it's del divergence of the gradient of temperature. Very good. That's Laplacian. All right. Now, once we have the governing differential equation, we need to have boundary conditions if it's only a function of space, or if it's initial conditions we need if it's a function of time as well. This is where most of you don't get it. It's not the specified temperature. That's our first type of boundary condition, where T is equal to some, at X is equal to T naught or Ts. It's not even the adiabatic or the well-insulated no heat flux boundary condition, where the derivative of temperature with respect to X is equal to 0, something like that. The hard one, what's the third one? The one that students will continue to ask me questions about later on, even after they pass this class, with an A+. They're doing some senior design project. They come back with questions. What boundary condition is the hard one they mess up on? Not the specified temperature, not the adiabatic or insulated or symmetrical boundary condition. It's the, okay, now I really shot you down. You don't want to talk to me at all. All right, I've embarrassed you. Here, I need to boost you back up, get your confidence back up. It's a convection boundary condition. And so what we'll have is we'll have a slab, a solid, over to this wall. And at this wall, we have, on the other side of the wall, we have a convecting fluid that characterized by temperature far away in the convecting fluid and a convection coefficient. And what we do is we introduce a very thin little control volume at that wall, and we say, what flows in must flow out. And we have a little conductive Q double prime conduction flowing in, and we have a little Q double prime convection flowing out. And because it's so thin, even if I have a transient problem, at any instant in time, what flows in from the right by conduction, in from the left by conduction must flow out on the right by convection without any accumulation. It's so thin, there's no mass, no thermal capacity for heating up that surface. Okay, it doesn't have any thermal inertia. So, how do you describe Q double prime conduction? By Fourier's law, minus K, derivative of temperature, with respect to X at that surface, equal to, how about Q double prime convection? H times the temperature at that surface minus T infinity. Does that equation make sense? All right. Then chapter 3. We spent a lot of time. We just finished chapter 3. We had a plane wall You have the temperature distribution in the plane wall. Nothing too surprising without heat generation. It's just a straight line, steady state. You have the thermal resistance concept, L over Ka. You can have multiple resistors, a network. You could have network, a series network, parallel network, solve for the temperatures at the nodes, solve for the flow, the heat flow through the system, the Q. Have composite walls. Have contact resistance. This was a little curveball, TC. This one, do you remember the SI units for that term introduced in our textbook? How about this? Go back. What were the SI units for this R where it's L over Ka? Is that degrees C per watt? Yeah. How about this one now? It's very close to degrees C per watt. Almost there. But they added a little m squared. And they didn't put it in the denominator, they put it in the numerator. But hey, that I shared with you. Don't think sometimes too much about that term. I prefer to do 1 over hc for contact conductance. But anyway, there is the contact resistance. Then we had for a cylindrical system, and we had the resistance for a cylindrical system where maybe I sketch it like this. Here's the center point. You go out to radius R1, then you go out to radius R2. So you have a layer of insulation from R1 to R2. And then that resistance in the cylindrical is natural log of. What is it a natural log of? R2 divided by R1 divided by 2 pi KL. Professor, do I have to memorize that? Well, it's in your equation sheet. Can you find it in your equation sheet? You should know what it looks like, where it's at. And then for a sphere, you have the same concept. On a piece of paper, it looks like the same R1, R2, but it's now a spherical coordinate system. You have 1 over R1 minus 1 over R2 divided by 4 pi K. All right, so you can do conductive networks in series where you have layers of insulation on a pipe or layers of insulation on a spherical tank, and that works as well. Okay, then we moved into this non-zero Q dot where you have energy generation. What are the SI units when you see that Q dot for this textbook? Watts per meter cubed. It's a volumetric energy generation term. All right. And then you can solve problems where you have the generation in the wall. You have this temperature if it's symmetrical. The maximum's here. If the temperature is not symmetrical, the maximum shifts toward the wall, higher temperature. Are the temperature solutions available on your equation sheet for that case? Let's say a wall with heat generation. Is T as a function of X available to you during the exam? I should have put it in there. Maybe I'll add it to an equation and write it on the board during the exam, okay? But I would refresh your memory. Out of Appendix C, they should be in Appendix C.
Yeah, I think it's on the first one.
That's where these equation sheets came from. Chelsea, she graduated last year. She did them, the equation sheets. All right. All right, so let's continue on. Then we just spent a lot of time in extended surfaces, and I want to solve a problem for that. That's my review. How many problems on the exam? 4 or 5. All right. Is it doable in 3 hours or doable in 1 hour and 15 minutes for the average student? 1 hour and 15 for the average student, meaning half of you, I got to take it out of your hand. Sorry. But I give you a little more time, maybe I take it out of fewer students' hands at the end of the exam. All right. Let's go on. Air-cooled heat sink is mounted on a 53 millimeter by 57 millimeter computer chip. So here's 57, here's the 53 millimeter, and they have this heat sink is put on. This heat sink has square cross-sectional pins. So looking down, they look square. Looking at the side, they just look long. Okay. So the square cross-section pin fins Each of them are 3 millimeter by 3 millimeter, this dimension here by that dimension, and they are 30 millimeters long. They're fabricated from extruded aluminum alloy having a thermal conductivity 175 watts per meter degree C. The air blows over the fins. The air temperature T infinity is 25, and it has a convection coefficient 125 watts per meter squared degree C. The base temperature is 75. Calculate the total heat rate from the array of pin fins. It's a heat sink with little pin fins sticking up, square, okay? So, in the interest of time, I'm going to talk to myself, and you just kind of listen in to the conversation. Isn't that called a lecture? Yeah, I think that's a lecture. Okay, so if I wanted to calculate Q, it would be, the basic equation would be get an H, get an A, multiply by the temperature difference, TB minus T infinity. But then somebody says, look, the base is at TB, but the whole pin fin coming out, down here, it may be TB, and right there TB, and right there TB, but not out here. And so the temperature's dropping as I go out that fin. So I better have some parameter, and we're going to call that eta naught. What's eta naught? Overall efficiency. It could be close to 1. It could be 90%. It could be 80%. Will it be over 100%? No, look for your error. Could it be negative? No, look for your error. But this is where most people would say, oh, that's the most difficult parameter to calculate. No, I challenge you. That is where a lot of students will make an error on an array. Because what is that A in this equation? It's the overall surface area. It's the total area. I don't like the subscripts used in the book, but hey, I think it's A total or something like that, AT. All right, so what is AT? Maybe it should be AO for overall, but isn't it the sum of two parts? What is it the sum of? The area of the exposed base, not covered up by any pins, plus the area of all of the fins. Does that equation make sense? All right, now you do me a favor, I'll walk around. I want you to give me the equation for the area of the exposed base for this problem. The total area of the exposed base for this problem. And then once you get that one done, calculate the area for all of the fins. Got it? All right, I'm going to pause, walk around. Yeah, this is the hardest part, isn't it? So what we have to do is, I would do this. I would say, okay, this is 53 millimeters by 57 millimeters, and that gives me millimeters squared. And then I have to subtract off that there's 54 pins covering each of them, 3 millimeter by 3 millimeter squared area. Now they'll give me the exposed base area. Make sense? Then the next one, all fin area. Well, I know I have 54 of them. That comes from this array. There's 54 pins. And then I'll have the perimeter, which is 4 times 3 millimeters. 4 sides, each of length 3 millimeters. That gives me the perimeter. And then I multiply by L. Now, that L is 30 millimeters, but I'm going to use a corrected length so I don't have to go and add in that, and I'm going to use that L sub C because it makes for a simple equation for the efficiency of one fin. So this L sub C I haven't quite calculated yet. We come over here, we do a little doodling. Let me add a new page, insert, new page. I come in and I say, my pin is a round pin attached like that, right? And so if it's round of diameter D, this is the physical length L. What is L sub C for that round pin? Isn't it L plus D divided by 4. Okay, somebody says I have a long rectangular fin. It goes back to the base like that. Its length L comes out, and it has a thickness T. What is my corrected length? L plus T divided by 2. And now we have a cousin. It's a square pin, and it's connected to the base, and it has length L going like this, and it has side, what do you want to call this? Let's call it S. It's S by S. It's square. Okay. The corrected length is going to be L plus S divided by something. Let's all guess. 4, 2. Okay. Now let's go back and let's get this formula. If I said I'm going to have the area using the corrected length, that's really, I want it to match the area of the not corrected or extended length plus the area on the tip. All right, this equation I'm going to apply for the round, the rectangle, and the square. Okay, so the area on the sides for the round, that's going to be pi dl. Are you with me? The area on the tip for the round is pi d squared over 4. That's a bad looking square. My pen has been doing that. Does that look okay? Are you with me? Thumbs up. Good. Now we're just going to use the corrected length, and it's going to have the right area. And so it needs to match what's on the right side of my equation. Pi d L sub c. This equation, I can cancel the pi's. I can cancel the d. And I'm left with the bottom line, the final equation. L sub c is equal to L plus d over 4. Make sense? Let's do it again. Let's do it again. For what? Let's do it now for this rectangle. So we want some equation using a corrected length, which is basically going to be, let's do this. What is the here? What is going to be the area and then the area of the tip? Okay. What is the area of the tip? I forgot to put in W. Didn't I? Okay, W. Area of the tip is W times T. Do you like it or not? Thumbs up on the area of the tip for this. Got it. Good. The area on the sides is going to be neglecting this little length here, and the other side is just going to be the L times 2W. How did you get the 2W? Why isn't it just W? Because I have the top and bottom. I neglect the little side, up and down. All right. Then if we use a corrected length, it'll be L sub C times 2W. Can we cancel the W's? Yeah. Can I divide everything by 2? Yeah. What equation am I left with? L sub C is equal to L plus T divided by 2. Bingo. Hey, we seem to be batting 1,000. Isn't that baseball jargon? If you're batting 1,000, that's great. Shown and shown. Now let's do this one. Okay. So we're going to have the area corrected, which will be 4 times side times L sub C, equal to the area on the sides, 4SL, plus the area of the tip, which is S squared. So L sub C is equal to L plus S divided by 4. Done? Done. So let's continue back to this problem. So this L sub C is going to be 30 plus 3 divided by 4. It's almost 31, but it's 30.75 millimeters. That's our L sub C. That's what we would put in this equation right here. And would that give me the correct area for all of the fins then? I add these two, I get the total area. That's the area right there. I think that's more error prone than getting the overall efficiency. The areas is more error prone. But now let's continue on this problem and let's get the overall efficiency. Isn't it 1 minus an area divided by an area? It's the area of all of the fins. Hey, we just calculated that. Divided by the area total. Hey, we just calculated that. I'm glad we did a good job of calculating the areas. Then we multiply that by 1 minus the efficiency of a single fin. Is that equation correct? Can you find that equation in your equation sheet? I'm going to pause, walk around. You put your finger on that equation in your equation sheet. All right, so in case you're going to chase some numbers on this, I think I have some numbers. Let me see if I can find them. So what is the area ratio? All of the area to the area total. That comes in at, I think it comes in at 0.8873. 88%, 89%. All right. Now I have to work on the efficiency of one fin. This is really getting easy now because the efficiency of one fin is using that corrected length, the TANH, I forgot the name of that, TANH, hyperbolic tangent of M. M, is that meter or my fin parameter M? Fin parameter M times L sub C divided by M times L sub C. So I already got my corrected length. I just need to get my fin parameter M. My fin parameter M is the square root of HP divided by KA sub C. I know there's a lot of theory and we worked that out before, but you don't want to have to go back to the governing differential equation every time you solve a problem. You'd like to go back, okay, I'll pick it up from here. We put in our value of H, which was 125, and then our perimeter, that's going to be 12 millimeters, divided by K, thermal conductivity, 175, divided by our cross-sectional area, 3 times 3, so 9 millimeters squared. You pick up that parameter M is 30.861 over meter unit. We then multiply by L sub C, and we calculate that the efficiency of one fin is around 0.7786, which then allows us to go back and get the overall efficiency for that finned array to be about 0.8036, about 80%. And this problem's over because you finally just calculate Q, 113 watts. Done. Little takeaway. I would start with this equation and I would focus on getting my areas correct first. Make sure you get the area. You may say, that's not even heat transfer, Professor. I mean, getting the areas correct, isn't this kind of like back in, pre-algebra? Yes, but don't make an error there. Get your areas correct. Get your area ratio correct. Then focus on getting that overall efficiency, which means you have to get the single fin efficiency, which means you get the fin parameter with that corrected length and you're home free. Any comments, questions? Can I press on? This exam, a lot of material in Chapter 2 is just differential equations. Can you get the right differential equation? That was one part of it. And then the second part of it, after you understand the differential equation, can you get a solution to the differential equation? So I would anticipate on the exam, either this type of problem, here's a differential equation, can you solve it? Or here's a physical description of a problem, can you give me the differential equation? Now, to get the equation and solve it may be too long if I want to get 4 or 5 problems on an exam. So I would pick one or the other. You will study both, and anticipate one or the other. True? So let's go and jump on this problem. And just look at the wording. Determine the differential equation that can be used to calculate the temperature distribution in the lead wire as a function of x. Ah, I'm getting a different. Am I going to solve that differential equation for this problem? No, just get the differential equation. So this is the problem. You have a transistor connected to a board, and the case of the transistor has a temperature Tc everywhere on it, right even where it connects to the lead. That's a temperature Tc. Then you have it connected to a board, and that's at a different temperature, Tb. I wonder why they chose C for a subscript on one temperature and B for the case and then board. All right. And they say that these lead wires bend up and connect them, and they pass electric current through the lead wires such that it generates some uniform volumetric heat generation due to ohmic resistance. That makes sense. A little bit of ohmic resistance, that'll be heat generation in our energy balance equation. Given a conductivity, uniform convection coefficient over the lead wires, surrounding air temperature, find that differential equation. How do you solve this problem? It's like a homework problem, wasn't it? How do you solve this problem? First of all, if they give you W in the illustration, stay with it. If they give you thickness, T, in the illustration, stay with it. Don't reinvent the wheel. Don't change it. And if they give you the starting location of X and going up, stay with it. All right? And so X is our coordinate system. It goes between 0 and it's going to end. At 0, it's at the board. At where it ends, let's call it L, because right here is a length L, is when it's at the case. So really my differential equation is going to be hard to get. My boundary conditions are really easy to get for this problem. The temperature at 0 is equal to the board temperature, and the temperature at the end of the lead wire is the case temperature. Those are my two boundary conditions, easiest boundary conditions. But now, how am I going to get my governing differential equation so that I can solve for the temperature distribution in the wire? Well, grab a little section of this wire, that lead, all right? So if I grabbed it, I'd look like this, goes back, and like that. I try to cut it out. And I have conduction and conduction. Now, because they introduced that as the positive direction for X, I'm going to be consistent and have Q flux at going in the positive direction and then going out in the positive X direction. Okay, we're going to have our X coordinate system start here at X and end at X plus delta X, somewhere going up, X plus delta X. Okay, so if I wanted to know the area that this flux is multiplied by, what is that area that the flux is multiplied by in terms of L, W, T, and what other parameters I'm thinking of? Wouldn't this be with W going back and thickness T up? So is that area W times T? Thumbs up if you agree. Good. All right, then coming out over here, we're going to have Q conduction out, which is equal to Q double prime times the same area. All right. Those are two ways heat flow in and out of this system. I also have heat flow this way. What do you mean by that way? Let me try and draw it a little better. What is that? It's Q convection. Now, I'm going to have the top and the bottom, so I'm going to have a 2 right away. Why the 2? Top and bottom. What's the area? The area is going to be W times delta X. Why isn't it W times T? No, it's W times delta X, isn't it? Then it's going to be the temperature at that location minus the fluid temperature far away. Remember, we're just going to be looking for T as a function of X. That's all. So at any place along here, it has the same temperature. It's one-dimensional heat transfer, or temperature is only a function of X. So that's my one convection from the top and bottom. And I have another in, and it's due to my heat source. So Q dot, that's a volumetric heat source. I was explaining to a student in office hours today. Show me the units on that Q dot. Is it watts? No, it's watts per meter cubed. Don't I need to multiply by my volume to get it into watts? And I'm doing this energy balance, and every term is in watts. So I multiply by volume. The volume of this is T times W times delta X. Isn't that my volume? If you did that, you followed all that, this is easy now. So you just do this. You could write it a couple different ways. The sum of the ins are equal to the sum of the outs. Let's do an in. Let's do a Q double prime at X. Maybe I should have emphasized. This flux is at X. This flux is at X plus delta X. They are slightly different, aren't they? Q double prime at X times W T, my area. That's an in. Over on the outs, I'll put Q double prime at X plus delta X times my area WT. Isn't that an out? That's why I put it on the other side. All right. The other in, Q dot times thickness W delta X. And then my out for convection, 2 W delta X T minus T infinity. Now what we do is we'll take this out and flip it over to the other side, and we're going to have a minus Q double prime X plus delta X times WT. Why did there become a negative sign? Because you moved it to the other side, true? And then what we do is we say, hey, I know how to compute the Q double prime. It's Fourier's law. So this is going to be the negative of the negative K times the derivative of temperature with respect to X at X plus delta X. And then you're going to have plus the same thing for Q double prime at X, which is minus K dt dx. This close that parenthesis at X plus Q dot. All of this is multiplied by that area WT. I should have canceled. Let's just cancel some of these area terms. That'll clean it up a little bit. Let's do that. So I'm going to get rid of I left out an H. There, that's why you guys don't like me. So you have plus 2H. And I left it out up here. Didn't I? Thank you very much for the correction. Let's go ahead and cancel our W's. And how about our T's? Let's just divide through by T, 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 T. Well, actually, I already moved that term over. So this becomes a divide through by T. All right. Forgot that W. Okay. So it's going to be this. And then I'm going to actually divide through by delta X. I'm going to put a delta X like that. All right. Equal to 2. Let me put H divided by T, and then T minus T infinity. Okay, at that point, does that equation look a little better? And then what do I do with this ratio right here? I notice, oh, that's my definition of derivative. If I let delta X go to 0, this is my second derivative, taking that K outside. And then I'll bring that K over, and 2H divided by KT, that's a K, T minus T infinity. You say, man, this sure does look like m squared T minus T infinity, the second derivative of temperature with respect to X squared. We've solved that problem over and over. That's our fin equation. What's the new term? Well, we had some heat generation in our fin. If you're a budding mathematician, you say, well, that's a non-homogeneous term. I don't know where they got this wording from, right? But it's non-homogeneous. So there's a whole strategy. First of all, we had the strategy of undetermined coefficients. But then we're going to add another part to the solution to cancel out that non-homogeneous term. But that's not what they wanted us to solve for. At this point, you just put Q dot divided by K, and there is your equation. Second order, non-homogeneous, linear, differential equation, and you had two boundary conditions, and you can then go on and solve it. Let me pause. Did I do everything okay? Or do you see anything else? All right. Let me see how much more time I have. I can squeeze this one in, and then we have a quiz, okay? We have a 400 millimeter long rod, so the length here is 400 millimeter. It's 25 millimeter diameter, so D is 25 millimeter. And it's made with a thermal conductivity K of 60 watts per meter degree C. It protrudes from a surface wall temperature of 200 degrees C, and is covered by insulation for the first 200 millimeters. The rod is welded to the furnace, so it's good contact. Thermally, that base of that rod is 200 degrees C. It's supporting some cable, instrument cable. The ambient air temperature out here is 25 degrees C and a low convection coefficient of 15 watts per meter squared Kelvin. Calculate T0. Well, what is T0? It's that temperature of the rod at the exit of the insulation, where if it goes further, then it acts as a fin. What is this showing about the tip of the fin? Insulated. It's insulated tip. Okay. How are we going to solve this problem for T0? I would put a network. I would say I know TW. I'm looking to solve for T0. And I know T infinity. And I know that there's a conductive resistance to the flow of heat, Q, from T wall to T0. What would be a model for this conduction? Is there any loss out into the insulation? No. It's just straight conduction. What is that resistance? L, insulation, divided by K, A sub C. A sub C is pi d squared over 4. It's the cross-sectional area for conduction down that rod. All right, what about out here? Well, I remember my fin equation, that Q fin is equal to some efficiency of the fin, some H times some area. I'm going to use because it's insulated, I don't need to use the corrected length. The corrected length is the same as the physical length. All right. Times that area. That area is pi dl, true? That's my convection area. Times T0 minus T infinity. Does this equation look good? You know, we can rewrite that equation and say, you know, that looks just like a resistance. That resistance is 1 over HA with the fin efficiency. You see that? It's just 1 over HA with the fin efficiency. Because I'm going to talk about the resistance 1 and the resistance 2. Is the flow through that first resistor, Q, is 50 watts, 75 watts, 33 watts, whatever it is. Is it the same as the flow through the second resistor? Or somehow the Q's don't match? The Q through the first resistor, is that equal to Q through the second? This is series. It's the same. It's the same. True? So the Q through the first one is TW minus T0 divided by R1. And the Q through the second one is T0 minus T infinity divided by R2. The only unknown I have in this equation is T0. I just do a little algebra. Maybe I'll take 2 or 3 steps to do it. Let's work it out. This is TW minus T naught times R2 plus T naught, equal to T naught minus T infinity times R1. Makes sense? So we're going to get that T naught is equal to T infinity times R1 plus TW times R2 divided by R1 plus R2. You've seen this so many times. If I look at R1 divided by R1 plus R2, it gives me a fraction, maybe 30%. Then if I look at R2 divided by R1 plus R2, well, if the first fraction was 30%, guess what the second fraction is? 70%. They add up to 100. It could be 50-50, 60-40, 30-70. Boom, the math works. Okay? So at this point, you could substitute the numbers, work out what the efficiency is. Let me see if I have any notes on this. And you find that T naught comes in at 109 degrees C. Well, in the interest of time, I need to stop there. Thank you very much. Zach is going to pass out a quiz.